In a conclusion, you start out by simply stating what you actually found, but more detailed than that, you actually want to state what was the relationship that you found, because that was the goal. So if I had a scientific question, for example, as shown in this graph over here, how does the height that you drop an object from affect the time it takes to fall? So I graph that out. I can't just simply stay, looking for the relationships, state as the height goes up, the time goes up, because that's fairly obvious. Yes, we understand that, but instead the relationship is what matters. Notice that as the height increases, right, the time does not increase in equal proportions. This is not a line here, y equals x. Instead, this is a square root graph. This is something along the lines of y equals square root of x. Now, this might take some time if you're a ninth grader to grow into this, but if you're a junior or senior, you should be able to pull this off by now to where you're able to look at the line and get an idea of what graph it is approximately. Now, this idea of what is the relationship and getting some sort of equation or predicting some sort of equation actually has great meaning whenever we come down here and we start talking about real-life application. So what is the relationship? Was your hypothesis supported or not supported there? You made a hypothesis. It was an educated guess, emphasis on educated there. Was it supported or not? And does it line up with previous scientific findings from your general research? Does this make sense? Now, after you state what actually occurred and you talk about your results, discuss what went wrong. By the way, discuss scientific findings, if there is a known quantity that you can compare against, actually doing a percent error there calculation would be perfect. So let's say if you're in my physics class and you linearize this and you see that the slope of the line can be compared with gravity, and gravity, of course, 9.8 or 9.81, then you can do a percent error analysis on that. But continuing to move forward. Second thing, after you discuss what the relationship is, discuss what went wrong. How certain are you of your results? I mean, how good do you feel about all of this? And you have to support it with evidence. You can't just say, this is great, I know it. Discuss the errors shown on the graph, and that's your error bars, right, on all the data points here. Look at where it intersects the y-axis. If it intersects someplace besides 0, 0, and that doesn't make any sense, well, you would want to talk about that. Is there any weaknesses in your procedure? As you got going, you noticed that you were having trouble whenever you were lining up and dropping, or you also noticed that, and we're going to talk about uncertainty in data here in a second, you also noticed that whenever you were on short distances, your times were all over the place there. I mean, you were dropping from a short distance and your average time turned out to be 0.2 seconds, but your actual error was plus or minus 0.2 also, and that's a very large uncertainty. So discuss any large uncertainty in your data, and then discuss why that might have occurred. Do you need more data to be sure? Did you get enough data points in here on all of this to actually be sure that your best fit line was good? Were your error bars on your graph very large, and so the only hope of figuring out if that's true is maybe you need to do more repetition, see if you can decrease the error through averaging. Finally, well, two more things really. Suggest some improvements. For every last weakness that you put down, you have to suggest a way to fix it. They need to be real suggestions, not some crazy thing here. So if you list a weakness, you got to fix it. Maybe using a table like this would be a good idea, where you actually list out weaknesses whenever you're planning on how to write up your lab, and then you list out your improvements. That way, whenever you write it up, you know that every weakness that you list has a improvement. Finally, and this is somewhat the hardest one, suggest some real-life application. Tell us why your results matter. To whom does it matter? Why would anyone care? So for my falling lab, for example, this is a big deal to anyone who deals with something that might fall, ranging from airplanes out of the sky. We sure hope not, right? But on the other hand, airplanes falling out of the sky doesn't have to mean just straight falling. It can mean gliding. And so Boeing or NASA landing space shuttles or anything else that they're dealing with dropping, they care about the rate of descent here. And this speaks to, if you don't actually create lift with wings, what is your rate of descent going to simply be? Because as you increase the height, the time does not increase linearly also. This means you are accelerating, going faster and faster and faster. So give us some suggestions for why your results might actually matter in real life. So in review, there are 4 pieces to a conclusion. You state what the relationship was. If you're in ninth grade, maybe you can get away with starting out with as one goes up, the other goes up, or as one goes, as your independent variable, your x goes up, your dependent variable goes down. But by the time you're a junior or senior, we're actually expecting you to use some insight and be able to talk about the relationship you're seeing in the graph. Discuss what went wrong, discuss all your errors, your uncertainties, and weaknesses. Suggest fixes to all of those weaknesses, and then talk about why your results might actually matter in the real world.